about some logistics. First of all, if you want a new seat, today is the day to do that, but you all look pretty happy and comfy in the spots you're in. I am the same way. I get really attached. When I was in undergrad, they had a language requirement at Carleton, and I chose to study Chinese, which was awesome. So I was in the same room 5 days a week for like 2.5 years, and I sat in the same spot every single day. So I completely understand that, like, you get attached. I get that. A reminder in case things got confusing for you, okay? And a reminder before the reminder, you can always send me an email. If you're not sure if something is due and you're freaking out, send me an email to say, hey, blah, 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 and I will respond to you as soon as I see it, unless you need something, and then I may need to be at a computer to do it, not just on my phone. But that all said, the Rotational Acceleration Lab spreadsheet is due tonight by 11:59. I've gotten at least one, maybe a couple of them already. But I want to make sure that you know that is due tonight. Please make sure that all group members' names are on the sheet. Okay? Please make sure that everything is labeled and clear. When your name is attached to that sheet, even if you didn't do it, in big air quotes, you are saying, yes, this is mine. So if you don't get full credit, then don't complain to me, I guess is what I'm trying to say. Does that make sense? You need to make sure that you're okay with it before 11:59. I'm not going to grade them until tonight, not tonight, tomorrow. Okay. But I'm just making that really clear. Okay. Every group member individually, is responsible for the information and needs to use it for your conclusion evaluation section. Okay. So to be clear, you do not need to write up the entire lab. You don't need to do the design portion. We worked on that a lot together, right? We spent lots of quality time on that, which is important, and I think it's really good, but you don't need to write it up for me, okay? You've spent time on the data collection and analysis stuff. That's what you're sending to me tonight. So for Friday, by Friday at 11:59, oops, I need to turn that for you so you can see it. This is what I'm looking for, okay? This is up on, I guess I have not updated the Canvas to try 3, but I'm going to do that today. So this will be up there by then, okay? But this is what I'm looking for. Given all of the work that you did, we spent like a day and a half looking at algebra, right? And it's not just because I wanted to waste time. You guys know that, okay? But it's because I wanted you to understand it. I want you to now write down a conclusion with justification based on what you see. So you're going to need to go back to your spreadsheet that you have access to, because it's a Google Sheet, so you've all got access to it, right? And you're going to look at it and you're going to say, okay, this is what we expected. This is what we see. This is what I learned. Okay? Unless you got exactly the same value for your slope as you expected, this is going to be the place where you talk about that. Okay? In aspect 2, evaluating weaknesses and limitations, human error is not the answer. Okay? I'm going to tell you right now that if I see human error, I'm just going to give you a 0 on that. Okay? Fair warning. Don't write human error. That's not the right answer. Okay? Every single lab investigation that you do can be improved. Okay? If you're working at CERN on particle physics and you're getting one proton to hit another proton and smash together to get stuff, even that lab can be improved. So if that lab can be improved, then PVC pipes swinging around in Iowa absolutely can be improved. Be specific. Realistic improvements to address the weaknesses and limitations. Does that make sense? This doesn't have to be pages and pages long, but it should address these 3 things. Okay? Doable? Okay. Cool. All right. So that I just wanted to make clear that's kind of where we're at for that lab. Today we're going to talk about conservation of energy. I will put this up on Canvas. It's not up there yet, but I will put that up there hopefully today. I am going to give you fair warning right now since we're starting trimester 3. I had more late work from this class than all of my other classes combined. I am done collecting late homework months after it was due. Okay? I get that sometimes you have a late track meet or you have to babysit your brother or whatever it is and you can't get it done that night. Now, let's be honest, you have all that stuff way ahead of time. So really, is that an excuse? I'm going to be generous and say sure. Okay. During trimester 3, I'm not going to accept late homework if it's more than 5 days after it's due. Okay. Questions about that? Okay. Awesome. Yay. All right. Any other logistical stuff before we get started? I've got a bunch of stuff to hand back to you, and I'll do that sometime soon. I do want to tell you also, because I don't want to forget to do this. So we're going to talk today. I was going to address Ian's question. He was asking me earlier, kind of what our plan is going forward. We're going to talk about conservation of energy today. Can I finish my thought, and then I won't answer your question. I will not be here tomorrow because I'm going to be presenting at a conference, but I will be back on Thursday. Tomorrow, you will be working on a applied problem, okay? I will record a little bit. I will explain it. You'll work on it. It'll be great. And I'll probably leave some other problems for you to work in case you need something to do. On Thursday, we're going to do angular momentum, okay, which is kind of a one-day deal. And then we'll reassess on Thursday to figure out what our plan is going to be. It is my intention between now and spring break, which is next Friday, right, a week and a half away, to assess this unit and also to do some sort of final or comprehensive test, okay? And I know that we were shooting for trying to do that early next week, but I would rather do it thoughtfully than just shove it all in, okay? So I'll look at that a little bit more carefully in the next couple of days and let you know. Does that sound okay? Okay. Pull out some notes. I'm going to give you a problem. I'm going to throw this up here. You've seen this before, but I want you to answer it now. Just kind of getting our brains back into energy here. I'm sorry, yes.
Yeah, we're going to get more of those late homework tips.
Yeah, then you don't need them today.
Okay.
I'll get them for you, though. Yep. So go ahead and take a look at this question. It's been a few days since you've done it, so you can do it again. Oh, good. I'm glad. Sure thing. Sounds good. Okay, so we've got 2 water slides at a pool shaped differently, but they start at the same height. 2 riders, Paul and Kathleen, start at rest. There are a couple questions. The first one says, which rider, Paul or Kathleen, is traveling faster at the bottom?
They're the same.
You say that they're the same. What is your, I'm just writing down what you say. Oh. What's your evidence? Conservation of energy. Right? Sure. You know that they're the same because of conservation of energy. So is that really a sufficient answer? I don't know. I mean, we could really work it out, right? We could say that the gravitational potential energy plus the kinetic energy at the beginning has to equal the gravitational potential energy plus the kinetic energy at the end, right? And we can say that there's none of this and there's none of this and this is MGH. I just want to make sure this makes sense to you because we're going to start doing this again today, okay? Equals 1/2 mv final squared. And then you notice that you've got an m on this side and an m on this side. So do the m's matter? Nope. So whether or not Paul and Kathleen are the same size, it does not matter, right? We know that the velocity of any object that starts up this high from RH equals 0 is going to be moving at what? 2 gh meters per second? Okay. The next question says, which rider makes it to the bottom first? That's part B. Did you talk about that one or not yet? Yeah. Okay, go. Tell me. Kathleen. Why do you say Kathleen? I just heard mumbles. I didn't hear an actual answer. Can somebody tell me the answer? Go for it. Take it.
She converts her potential energy to kinetic energy sooner.
She converts her potential energy to kinetic energy sooner. Does that make sense to everybody? Yeah. So she has a bunch of potential energy at the beginning. And that gets converted to kinetic at a faster rate, which means that she travels more of the path at a faster speed. And so therefore she must be able to get down there faster, more efficiently. Okay? So my question for you then is, if Paul and Kathleen were on like side by side water slides, regardless of whether it was this funny one that looks like it would be really frightening or the lower one that Kathleen is on, they're going to get there at the same time, right? Does that make sense? Does the mass matter in that question in terms of who's going to get there first? Did that question make sense? And the answer is no, it's not going to matter. Okay. Oh, wait, what?
You just said that they get there at the same time.
If they're both riding the same slide.
Oh, yeah.
So if they're both on Paul's slide, or if they're both on Kathleen's slide, or if they're both on any slide, as long as it's the same slide, then they're going to get there at the same time. That's what we're saying? Okay, cool. All right, so I'm going to pause this for just a second. Please hold. Okay. So let's write down what we saw just so we don't forget, because that was a wonderful little conversation, but when you get home, you'll be like, I don't remember what happened. So we had a ring and a disc and a large disc. And when we put those all on a ramp, well, that's a really steep ramp. So you had like one, and then you had another one, like that. And they were going to go down here, and they got to the bottom at different times and whatever. Remind me what happened when we did the ring versus the disc. Who won? The disc won. And what was the reason that we decided that happened?
Small and moment of inertia.
Yeah. And then we had large disc versus disc. And which one won in that competition? The small disc? Again, because it had a smaller moment of inertia. Okay? So just to kind of like remind ourselves so that we know that this is all true. Now, not only do we like to watch things race, we need to understand a little bit more about them. So we said that was true, but can we talk about that in terms of energy, since that's the topic of the day? What kind of energy does that disc have when it's at the top of the ramp? Gravitational potential, right? Now, as it slides down, if we were just doing a box on a frictionless surface, a box sliding down, all of that gravitational potential energy is going to turn into what? Kinetic, just plain old regular kinetic energy. So again, if it was just a box sliding down, then we'd have the gravitational potential that turns into the kinetic. I'm going to write that as translational kinetic because there's another piece that goes into this puzzle now, right? Box sliding down is just going to turn gravitational potential into translational kinetic. What's fundamentally different about the things that we're doing now? They're rotating. Now, you remember when we talked about that carousel, right? Those kids, if they went all the way around, there was no displacement. But there is some motion, some translational motion as it goes around and around and around, okay? So what we can do here, and it's funny because we're not like defining new energy, we're just talking about it in a different way. We're going to take that motion energy, that kinetic energy, and talk not just about, oh my gosh, come on. Not just about what we call that translational kinetic, which is represented, K is equal to, what was it? From so long ago. Okay. We can talk about it in terms of rotational kinetic energy as well. If you have something in rotational kinetic energy, it's still moving. Okay? It's still got mass and it's still moving. But usually when we're talking about rotational kinetic energy, instead of talking about the translational velocity or that tangential velocity, we talk about it in terms of angular velocity. You with me there? Okay? So we're just going to switch it out. So rotational kinetic energy, it comes from the same place. So I'm going to start with K is equal to 1/2 mv squared, but instead of the V, how do I get an omega in there? How are V and omega related? Omega times radius equals V. I'm just going to remind myself of that in case I've forgotten. Omega times radius is equal to velocity. That's just a friendly reminder from last trimester because it's been, 2 days or something like that. I'm going to write that as R omega, but that's all going to be squared. Is that okay? And then I'm going to say, oh, but look, I want something just in terms of omega. Just going to keep writing here. I'm going to say 1/2. I'm going to change where my parentheses live. MR squared, omega squared. And what's so exciting about that? That is the moment of inertia. We're not changing anything. We're not reinventing anything. We're just looking at kinetic energy in a little bit of a different way. If something is rotating, that means if it's just rotating, it means it has kinetic energy, but it's rotational kinetic energy. And we're talking about it in terms of the thing that we talk about rotational motion in terms of, which is omega. So we can say that rotational kinetic energy, I'm just going to write that as K sub R, is equal to 1/2. That's really just the moment of inertia times omega squared. This is the rotational equivalent to the translational kinetic energy that we know and love. Okay. So if we then want to figure out kinetic energy of an object that's rotating, we can find the moment of inertia. So that might be mr squared if it's just a point mass, right? Or if it's something bigger, then we may need to use our fancy little sheet, okay? And again, you don't have to have these memorized. If you want to do the calculus to do the integrals, I can show you how, okay? Or here's the cheat sheet, okay? And it's right here, and it'll tell you exactly what your moment of inertia equations are. So this is going to be your star thing for the day. That's exciting. Yay! I'm going to give you some problems to work here because we've got just a few minutes, okay? A couple of ranking tests and a couple of things. Or do we want to do the math? Do you want to see how they compare? How fast they're going at the bottom? I want to do that, I think. Let's do that first, and then we'll rank stuff tomorrow, maybe. So here's the setup. It's the same ramp we had before. You've got 3 objects. One is a box. One is a disc. And one is a hoop or a ring. Okay? I'm going to say that they all have the same mass. And the question that I'm going to ask you, so we're going to rank them, I guess. So it is a ranking task. It's just not an official ranking task. It's a carbling ranking task. Which one's going fastest at the bottom? Can we figure it out? Do you have a question? Are you guys good? No? Who's going fastest at the bottom? Yeah. It is a box. It's just a square. It's not going to rotate. It's just going to slide down the ramp. Does that make sense? So the question is it frictionless? So here's the situation, and this is where it gets a little bit, I was about to say sticky, but I didn't mean that to be a pun, but I will now because I did. Okay? It gets a little bit sticky, and that is that a box needs a frictionless surface to slide. Okay? If the surface is actually frictionless, then objects can't rotate. You have to have a little bit of friction there in order for objects to rotate. That's why if you're trying to start your car while you're sitting on a sheet of ice and you hit the gas, your wheels are just going to spin because they have to have friction to grip. You with me there? So we're going to say that it's a situation where it's frictionless between the box so that it can slide. Okay? So you've got like 2 equal tracks, let's say. So you've got a nice smooth track for that box to go down, and you've got a sticky enough track for these 2 things to rotate but not to lose a lot of energy. Is that fair?
Scientists discover new
Woo! Semi-frictionless surface, or two side-by-side tracks. Like Paul and Kathleen have those side-by-side tracks, kind of same deal. All right. I want to know who moves fastest, because just like we did with Paul and Kathleen earlier, we said, who's going to get to the bottom first? We did that problem already, right? Pretty much. I want to know now who's traveling faster. That's the question. Okay. How are we going to set that up? Should we do the one that we know and love easily? Quickly first? Let's do the box. Okay? So we've got some height that we are above this surface. That's supposed to be flat. How'd that go? Not well. Okay? And we'll put the box on there. We know that energy at the beginning, E total, at the beginning has to equal E total at the end. What kind of energy are we dealing with when we're talking about the box? Translational and gravitational?
They're not gravitational.
KT final. Okay, just getting into good habits here. So this is MGH initial is equal to 1/2 MV final squared. So this is again for the block. We can say that the velocity is going to be equal to the square root of 2GH. Hey, it's like we just did that problem earlier today, didn't we? Which one do you want to do next? Aiden, you get to pick.
I guess like the ring.
The ring? Let's do it. Where are we going to start? Same place we did last time, Miss K. Okay. Total energy? At the beginning has to equal the total energy at the end? What kinds of energy do we get to play with this time?
Gravitational potential.
Gravitational potential. Rotational kinetic. Is there any translational kinetic?
Yeah. It's going down.
What does it mean to have translational kinetic energy? We haven't really talked about this. If I take this object and I throw it, right? If I just throw it, it's moving. It's got kinetic energy. You with me there? Okay? If I take it like this and I just spin it, that doesn't work very well. If I just spin it, then it's got rotational kinetic energy. If I roll it, what kind of energy does it have? Both. It's got rotational and it's got translational because the whole thing is moving as well. Yeah. So we've got rotational and we've got translational. At the beginning, there's no kinetic at all. At the end, there's no gravitational. Here we go. So we've got MGH initial has to equal. So all we're going to do is take these things that we know. It seems a little intimidating the first time you do it, but as long as you take a deep breath, follow what you've set up, you're going to be set. Okay? It's all right there. So the rotational kinetic energy is 1/2 I omega squared. We know that from the last page that we were on. And we've got 1/2 mv squared. Those are both at the end. So this sometimes looks scary, like, oh my gosh, now I didn't know what omega is. What? That sounds nuts. I want to know some translational stuff. But lucky for us, we know that omega is equal to what? Is it related to R's and V's? Velocity divided by radius? Yeah, for sure. So now, and oh yeah, then we need to know what I is. So we're going to look at our handy dandy chart that you can either pull out or you can trust me. Either way, if you want to, it's up to you. The ring, the moment of inertia for a ring happens to be mr squared. So that's convenient. Okay, so here we go. So we got mgh at the beginning is equal to 1/2 mr squared times v over r all squared. You with me there? We okay? Okay, nice, happy things are going to happen here. Plus 1/2 mv squared. What happens to my r's? They're going to cancel. So really, on the right-hand side, I've got 1/2 mv squared plus 1/2 mv squared. That gives me mv squared. Isn't that kind of cute? So about half of the kinetic energy, think about this. Hold on, let me say that again. What? You've got total potential energy, right? This is how much energy we have. For the ring, half of it is in rotation. Half of it is in translation, okay? And so the velocity that we get here is going to be equal to the square root of g times h. All right? Is the disk going to be pretty similar? Similar story, except that I is different. For the disk, is the moment of inertia going to be bigger or smaller? It's smaller. We know that inherently. If we look at our handy dandy sheet, we can see that for the disk, I is equal to 1/2 mr squared. That means that down here we've got mgh is equal to 1/2 times 1/2 mr squared times v over r squared. That's a lot of squares going on. Plus 1/2 mv squared. And so from this, you can see that now not all of the energy, or not even half of the energy, is rotational, which means more of it can be translational. Okay? Masses are canceling and all this stuff. I hope you guys are seeing that. I don't want to freak you out here. GH is equal to, so that's going to be 1. So that's going to be mr squared plus 1/2 mr squared. I could do that one in my head. 3/2 mr squared. Oops, it's going to be mv. Those are supposed to be v's. You guys got to call me on that. Sorry. What did I do? Hold on. Oh, I'm sorry. This should be a fourth. I'm sorry. That should be 3/4. My bad. I apologize. I don't even know what. No excuse for that. Just watching the clock. Freaking out. mv squared. GH, thank you. So V is going to be equal to then, what, 4/3 GH? How are we doing? Who goes fastest?
Box.
The box is going to go the fastest. Why?
It's got a bigger coefficient.
Why? This is a good Physics 1 question. Why is the box going faster?
Doesn't have to split its energy.
Yes, it doesn't, because they all have the same amount of potential energy at the beginning. Are you with me there? In all three cases, if the masses are the same, they've got the same amount of potential energy. That total amount turns all into translational kinetic for the box. But for the ring and for the disk, some of it turns into that rotation to get it to actually move. Okay? Last question, because we've just got a couple minutes. Here it is. Ranking task. In each case, a 1 kilogram object is released from rest at a height that's 2 meters from the bottom. So this is very similar to what we just looked at, right? All of the spheres roll without slipping and all the blocks slide without friction. Okay? Rank the maximum height of the objects on the other side of the ramp. So we're assuming no losses to heat. I just want to make that really clear.
Yeah. Isn't the box going to form the curve?
We assume that they're drawn not to scale so that they all can make the, yes.
So the box isn't just going to hit it.
No. And jumps off. No.
The corners of the box disappear when it gets to these.
Yes. Or the curve is big enough so that it, yeah.
Curves are different.
Talk to your table.
They're all the same height. And they're all the same height. Yeah, they're all one foot.
They all start up the same height.
They're all the same height.
They all have the same mass. Rank the maximum height.
Yeah, this square will go right.
That's the answer.
Yeah.
Why?
They stop. A lot of these, when they get to the top.
Did you guys all hear what he said?
Yeah.
Yep. All that potential energy turns back into potential energy, right? Yep. Same amount of energy the whole time. Have a great day, you guys. I will see you Thursday, but I'll leave something fun for you to do tomorrow. Bye.